So the table of contents is going to be a very short web caching 101 so that we're kind of on the same page about what we're talking about. And then we'll talk about 3 attack methods that are web cache deception, edge side include injection, and cache poisoning. If you're neither on the red team or the blue team, I still hope that you can get something out of this, even if you're just a developer, for example, just to kind of detect like that weird thing in your web app that sounds weird and that you might find a way to exploit just by watching this talk. So hopefully this is kind of suitable for everyone. So this short 101. So what is caching anyway? So you can imagine the most simple HTTP transaction that is the following. So you have your user, you have your cache server, and then you have your web server. The user sends a request which hits the cache server, and then of course the cache will first look at its internal memory. Like, have I seen this file before? And if so, well, perhaps I should send the version of that file back to the user. And in that case, it's never seen the file before, or maybe because the time to live for that specific file has expired. So the cache server has to reach upstream to the origin server to fetch that file. And then once it's received, it can commit it to memory so that the next time someone receives the same file, you don't have to go and fetch it from the origin server. So you just sped up everything by a great number of times. So it's amazing. So that's it. That's caching 101. You don't need to know more than that just to think about attack patterns in terms of caching. So let's talk about web cache deception. Web cache deception kind of flew under the radar, in my opinion. It was published in 2017 by security researcher Omer Gill, who demonstrated it using, I think it was the public bug bounty for PayPal. So if you were using InfoSec Twitter in 2017, you're most likely seeing the video where Omer used web cache deception to attack PayPal, and we'll talk about what that was soon, but the only thing that you need to know about web cache deception is that it's deceptively simple. And at first, it looks like it's not even that important because, sure, it's kind of bad, but how do you leverage it? Well, this is kind of what we're going to talk about today. So what web cache deception is a kind of neat trick that is going to abuse URL-based caching in order to have users' sensitive information cached. And how's that possible? Well, as an attacker, you're going to want to have this user that you're targeting visit a very specific targeted URL that you made up, basically. And the cache server is going to be kind of confused, and it's going to take the content of the HTTP response and cache it way too aggressively, and cache it in a way that the caching server thinks it's a static file. And then everybody else, after knowing that specific URL, can just go and get that file, which obviously is not meant to be cached. So how does that work? So imagine the following URL that is being requested by a web browser. So you have your example.com/profile security question, and the server that receives this sends back the following headers. So you have your HTTP OK, and then you have cache control, no store, no cache. So what this means is the cache, well, the origin server, the web application server, is telling both the cache server and the web browser, please don't store this. This is not meant to be cached. And since there's no static extension at the end of the file, like CSS or JPEG or GIF, the cache server decides to respect this because that's the way it's supposed to be, right? But then what happens if someone requests the same file but suffixes it with a static file like a.jpg? The application server sends the same response back, so don't store this, don't cache this. Either the browser or the cache should do that. But then the cache sees that it's a static file extension and loses it. It says, wow, that's a JPEG, I should probably cache it. Screw those headers. And then the content of the security questions gets cached too aggressively. Now, as an attacker, you can most likely go and fetch a.jpg, and you're going to have the HTTP response back without having to be authenticated or anything. So using the same diagram, you can see that the user being tricked into requesting the same file with a.jpg at the end reaches the cache server. The cache server notices that a.jpg has never been seen before, so it fetches it upstream from the origin server. And then the origin server responds back, and then it's committed to memory. So then when the response is back, it's sent back to the user. At that point, the cache server has cached a.jpg with the content of the security questions. So then as a malicious attacker, you can just go ahead right underneath and just get a.jpg and obtain the security questions. So that was like the example that Omer gave, which was, in my opinion, really interesting. But then I started thinking, like, what can you do with this? How do you leverage this into something that is kind of real world possible? Because it would be a terrible design to have the answers of your security questions sent back in the HTTP response. That would be just unsafe. So nobody does this, I hope. So when you cache something, think about it. Like, what do you have inside of all pages that are sensitive? Well, you most likely have CSRF tokens, but you can't really use them. So say here I could obtain CSRF tokens, then attacker in the step down there does obtain the CSRF tokens, but you can't submit the form because you're not logged in. You can't do anything with them. So you'd need a two-stage solutions, right? You need to have the user get their information cached, and then you need to do the actual CSRF attack. And this is what I came up with. So I have a two-stage solution where the first file that the victim is going to visit on my attacker-enabled server because I tricked them or whatever, I'm basically going to make their browser visit the very specific URL. And here you have the same pattern, right? Instead of a.jpg, it's just a random number because we're targeting a lot of users potentially. And then when the user has had their information cached, because the first step did the whole web cache deception trick, you want the victim to reach you again on a different page. And the reason why I did that is because from the step where I have their information cached to memory and the step where I am getting the CSRF tokens from the origin server, I need to buy time, right? I can't just do one after the other because it takes time to go and do the curl request from my server. And I probably could have used like Ajax or WebSockets to do a single page attack, but I'm pretty lazy. So stage 2.php, you basically get the same random that the victim had committed to cache, and then you go and do that curl request. So you go get the version that has the CSRF tokens inside of them, and you carve it out. You get those CSRF tokens, and then you send back to the victim that has requested page 2.php the CSRF attack with a pre-filled CSRF token. So you basically just remove the whole CSRF token mitigation. And that's extremely powerful because at that point, as you can see, the form can just change the security questions. And that could also be change password or change anything, like send money, it doesn't matter. CSRF tokens are just not a question anymore. You can just bypass it. So that's extremely powerful. So to illustrate how this works, because I'm a very graphical person, so you have your user who reaches our attacker-enabled server that I called evil.com, and then evil.com sends back the response of the image tag and the source tag, the script tag to the user, and then the user gets their information cached. And then at that point, you tell the user, please give me some time to go and get your CSRF tokens, so reach me back on a second page, which it promptly does. And then at that point, you can go and get the CSRF tokens from the cache server, send it back to the CSRF attack to the user, and then force the user's browser into changing their security questions. So that's basically what I came up with web cache deception, and you can use this on vulnerable servers. So the impact obviously is limited by your imagination. That was a very short example using a regular form with CSRF tokens, but you could also abuse, for example, admin panels. Like if the admin panel is on /admin and there's some sort of thing that says you need to be logged in, well, you could potentially do admin.a.jpg and then have the admin visit this, and then admin/a.jpg is now available to you, and you can look at what the admin panel looks like. So that's kind of interesting. Let's talk about why web cache deception is even possible in the first place. The pattern that Omer talked about in his white paper was using Django, and you can see the following vulnerable Django code. So you have your URL pattern, and the way that Django does things is that every URL endpoint is basically a regular expression. So here you have your caret, which means this is where I want it to start matching. But then if you notice at the end, there's no ending match delimiter, meaning that anything after questions will still match this endpoint. So you could have security questions, ABCD, it would still get triggered as requesting security questions, and you don't want that, obviously. So very simple fix is just add an ending delimiter, meaning that everything after security questions is going to not hit this URL pattern anymore, and the cache server is going to receive a 404. That's it. That's not harder than that. So yeah, your application server should definitely not send a 200 OK to garbage request. That's an easy fix. And it would be kind of nice if the cache server would not ignore our caching headers, but that seems too complicated for our industry. So Cloudflare's solution was really simple, but awfully effective. It just added a simple if statement, or I don't know if it's an if statement, but a simple thing to their algorithm, and they just said the file type, so JPEG, should also match the content type, which should be image.jpg. If it doesn't get cached. So if you have a.jpg, in this case, would return text HTML most likely. So it's not image.jpg, I won't cache it because it's most likely someone doing web cache deception.
The file type just means extension.
Exactly. So that's a very simple solution, and it works pretty well. If you want to do detection of this sort of thing in an automated manner, you can use the burp scanner. It's called the Web Cache Deception Scanner. It's by TrustWave. It doesn't have any fancy GUI, but it works pretty well. It's a simple test, but automating it is really powerful, so you can use that. So that's it for web cache deception. It's pretty easy to understand, but you can see how caching can get really intense. So the next thing we're going to talk about is edge-side include injection. It's a vulnerability that is close to my heart because that's research that I did for my past employer, and I really learned a lot about that, and I'm excited to talk about that today. So let's talk about what is ESI before talking about exploiting it, right? It's a cache specification that was introduced in the early 2000s when the web was starting to scale at unseen amounts. So people needed a way to have caching that was stronger and more reliable than we ever had before. So what they wanted is a way to have caching that is, in a way, malleable, like a way to modify cache at runtime. So what the specification brings, if you implement it correctly, is it gives the control to the application server the rights to modify the content of the cache in real time, sort of. So through ESI, you're kind of able to cache dynamic files, you can invalidate cache entries, you can even take decisions on the user states, say based on their cookie or their user agents. So a brief example of how that would look on a real example, a real website. Let's look at this very simple weather website. So you have just a weather website and then the forecast for Montreal. So you can see that it's really cold in Montreal, but also that this is a very simple example, and that to the end user, this is just a regular HTTP response. There's nothing alarming there. But to the ESI-enabled caching server, this might be multiple fragments. And these fragments are going to vary, or they could vary, based on multiple factors, such as where the content was fetched from, how long they will be cached for, or even should they be cached, right? So Montreal could be cached for 1 hour, but then the actual forecast data, like -12 degrees, should be cached for 15 minutes or 20 minutes. And then the weather website and all the labels could be cached for 1 month, because when you think about it, that's not likely to change anytime soon. So you can kind of see every single aspect of a web page as being a single fragment that is cached for different amounts of time. And at the time, that was amazing, because taking decisions at the cache level is kind of edge computing, right? It means that you're offloading something to the cache server or your load balancer, which is a HTTP surrogate, and then your application server kind of doesn't control the whole flow anymore. It's like they're working hand in hand. So that was something kind of cool for the early 2000s. So how does ESI work? You have two features, or at least two features that are widely implemented, and we're going to be talking about those today. So you have ESI includes and you have ESI variables. ESI includes are very simple. They're basically just single XML tag that say, please include the content of this URL. That's it. You could have more stuff like time to live or any other, like every specification of ESI has more arguments that you could pass to it. But the simplest way is just ESI include and then a source tag. And what it does is it's going to search and replace the content of that tag at the cache level before sending it back to the user. So then in that case, once the cache receives this, it's going to go and fetch API.local/Montreal Monday, and it's going to send back the content of that HTTP response inside the HTTP response to the end user. So to once again illustrate how that would work in a nice graphical manner, so you have your user, you have your cache server that is ESI enabled, then you have your web application server and a third-party application server. So your user requests index.html, index.html has never been seen before, or maybe the time to live is expired. It doesn't really matter, but the cache server decides it's time to go and fetch it again from the origin server. Now, the origin server sends back the response for index.html, but the developers added ESI tags in the HTTP response. So this response needs to be parsed at the cache level because it needs to act upon it because it's ESI enabled. So that ESI tag is going to generate a side request to the API server by issuing the GET request through menu.html. And then once that is obtained back from third-party API server, the steps 5 and 3, their HTTP response, are basically going to get concatenated together through search and replace. And then you can send a single HTTP response back to the user. So that's a very simple ESI include. We also have ESI variables, which are even simpler. So they have no attributes. Basically, all they do is they're going to expand a dictionary set of data that is going to represent metadata about the current HTTP transaction. So in this example, you have cookie, city, just put it inside the HTTP response. And once it is sent back to the user, the cache server is going to see this tag and it's going to replace it with the content of the cookie. So that was kind of interesting because at that point you could say, if, I don't know, cookie language is French, then reach the French version of our API. So that's edge computing in a nutshell, basically. So now we know about ESI includes, we know about ESI variables, so what can we do with this? Well, this gives us two facts. We know that ESI tags are sent inside the HTTP response, and we know that the engine is going to process the HTTP response, and that kind of means one thing. If you control the HTTP response, you control the ESI engine, and by definition, the cache server. So that's kind of huge. When you think about it, it's like XSS, where if you control the HTTP response, you control the HTML, and by definition, the browser. But we're not attacking the browser, we're attacking the cache engine, which in my opinion is much more dangerous. So you can imagine the following snippet, which is vulnerable to pretty much anything. It's just reflecting whatever you put in the city get parameter inside the HTTP response. So what would happen if someone was to put a ESI tag inside that get parameter? Well, the application server would just take that ESI tag, put it inside the HTTP response, and then the cache engine would see that response and acts upon that ESI variable tag. So it's going to send it back, and as you can see inside our response, we have our PHP session ID cookie. And that might seem like I'm repeating myself, but one thing to remember, if you've done any PHP development in the past, I don't know, 15 years, is that PHP session ID has this neat little trick, which is a security cookie, security flag on the cookie, meaning that it's HTTP only. And that means if you are JavaScript, you cannot reach the content of that cookie. So multiple people would just see this vulnerability and be, well, I can do a XSS, but then it's kind of limited because you can't reach the content of that cookie because of the security flag. The neat thing is that ESI doesn't care about security flags because the cache server, by definition, could not see those flags. Maybe the cookie was set 15 days ago and the cache server has been refreshed, so the cache server just decides all cookies are fair game. So you can get the content of HTTP-only cookie flags inside the response, and that's kind of awesome. So different ESI implementations, all ESI implementations are kind of different. So for example, sometimes you'll have to use the whole header for a cookie. Sometimes you can actually carve out the individual cookie through ESI. So that means that we're going to have a way to potentially do account takeovers. So that's kind of cool. And that's what we called ESI injection. So we kind of discovered ESI in late 2017. It's a colleague of mine, Laurent Desaulniers, who works at GoSecure. He was tasked with doing a proactive engagement. He was sent out to one of our major clients, which is a big ISP in Montreal, and they wanted a cache overview of a configuration overview of all their cache. So they had a whole bunch of cache. I think it was Varnish. And the only thing that we kept seeing inside the configuration files was that they kept using ESI, but no one's ever heard about ESI on our team, and we're all pretty good at web pen testing, or so we thought. So I started looking into ESI, and basically everything that I did from the end of 2017 to the April 2018 blog post is get my hand on all ESI specifications that I could find and just find 0 days in them and just try and break them or see how they could be abused and where they're being used. And if you want to learn about how that went through, you can look at the blog post on the GoSecure website. I'm going to give you, I think, one use case of that today. which is a cool use case. So we talked about the PHP session ID cookie, but not quite how we could obtain it, or at least how we could obtain it in a smart way. So this is a snippet that, when you think about it, is pretty efficient, right? You have an image tag that points to my attacker-enabled server, and there's this neat ESI trick in there that is going to take the whole cookie header, which might contain HTTP-only cookies, and add it in the search and replace way. So once the application server sends this back to the cache, the browser will receive this and then perform a GET request to evil.com because it thinks it's going to fetch an image. But it's not fetching an image, it's sending me your session ID. So how could we leverage this? We're going to be talking about that. But first, let's think about the impact as a whole for ESI. So ESI, when you think about it, is allowing you to do transparent session hijacking. And what I mean by transparent is that the browser is not even necessarily responsible for this, because you could have an ESI include that is including evil.com. So like in the previous example, we were doing just an image tag that the browser was sending me, but I could have done ESI include of an ESI variable, so then the cache server would send the content of the cookie to me, and then the browser would never have seen this attack. But that's kind of rare to see, and this one is much more broad. So even if you don't do transparent session hijacking, you can still do JavaScript less cookie theft, right? Because image tags don't require JavaScript. So a lot of people will say, I'm much more browser if I save the web without JavaScript. I say no. So you also have server-side request forgery. When you think about it, ESI includes is just server-side request forgery as a service. You can include any URLs you want on the cache server. So sometimes in clients, we'll find ESI include injections, and that server is not isolated because it's a cache server. It needs access to a whole bunch of things. So you can potentially do ESI include of the intranet or whatever other server. We can also do defacing, header injection, and a colleague of mine even found a remote code execution using an ESI specification that was using, I think it was unsafe XSLT processing, and I thought it was super awesome. So now let's talk about defacing, because that's funny. So we looked at Oracle WebLogic because, well, Oracle is a nice target, in my opinion. It's kind of high profile. And also, we saw that they implemented bonus features. And I call them bonus features because they're bonus features for your attackers. So looking at the documentation, we found the following snippet of documentation. It says the ESI inline tag marks a fragment as a separately cacheable fragment embedded in the HTTP response of another object. I don't know what any of that means, but looking at the snippet that they put underneath, you see that it passes a URL and that you can potentially put HTML code at that URL. So I was thinking, did Oracle just give us the easiest way to take over cache entries and potentially deface the whole website? Well, yes, they did. So we deployed an Oracle WebLogic server, and we put Oracle Web Cache on top of that. And that took like 1 week because Oracle does not want you to deploy their services. And we did an ESI inline pointing to /ping, and then we expected pong back. And we got pong back. And so we kind of found out that ESI inline tags allows you to create or rewrite cache entries on the fly. That's insane. And we also noticed that it's possible to commit further ESI tags to the cache, meaning that you could overwrite the content of index.html, and then inside of index.html put more ESI tags so that the next time someone goes to index.html, they're going to have a nice alert of the HTTP-only cookie pop back to them. That's highly confusing. And we kind of wanted to find a way in a real-world scenario to extract that cookie to our server without anybody noticing. So like a stealthy attack scenario. And we came up with the following. So when a website is using jQuery.js or any library for that matter, what we do when we found ESI injection is use this neat little trick where we're going to effectively backdoor jQuery.js at the cache level. So we're going to take the content of jQuery, put it at the bottom of the file, and at the top of the file, we're going to prefix it with a very simple AJAX request, which is going to expand the content of their cookie and send it back to us on our attacker-enabled server as a GET parameter. So once we have this particular snippet parsed by the ESI-enabled server on the cache, this is going to get committed inside of jQuery.js. so that the next time someone refreshes any web page on the server, js/jquery.js is going to be served as is, like this. Then before sending it to the browser, obviously the cache is going to notice that there's more ESI tags, and it's going to search and replace them, and then the AJAX request can be sent to the user. Now that way, the user is going to receive this neat little trick, which is going to send us the content of their cookie, but also jQuery is going to work as expected. So then you can just exfiltrate everybody's session without anyone noticing, because the cache is now poisoned. Okay, so now let's talk about detection. As we said, I touched on that a little. There's a lot of ESI implementations out there. They vary in terms of complexity and in terms of implemented features. Some of them even have security features enabled, like I think Yahoo Traffic Server, which is now Apache Traffic Server, is probably the nicest implementations of ESI right now, but still, like, go look at the blog post. There's a lot of details on how to exploit the particular version you're doing and also how to fingerprint them. So you can use any of them. You have Burp Active Scanner++, which I think was the first one to detect ESI. And then Burp Upload Scanner came up a few days after, and then Akinetics and Qualys, I think, took them like months to implement it. But still, they're all pretty good scanners. So how do you mitigate against edge side included injections? Well, obviously, you could encode HTML entities. I mean, it's an XML subset. So if you have XML tags, usually it's for cross-site scripting. So you probably already have the defenses in order not to be exploitable by edge-side include injection. But when you think about it, you have to be proactive about your escaping methodology, because do you ever encode HTML entities in JSON responses? I know I don't, because there's no need to do that, right? The browser is going to receive a text JSON response, so it's not going to parse that as HTML, so nobody's really doing HTML entity encoding in JSON responses. But then an attacker could just change their full name for an ESI include tag, and then have that sent back to them through the API request for their profile, and they're going to get the content of the ESI tag that has been parsed. So you can do server-side request forgery in arbitrary in arbitrary content types. I think there was I think it was Squid or something, that looked if the first character was a greater than symbol, and if it wasn't, then it just said, okay, it's not HTML, so basically it's not going to be something that is going to have ESI, so you can't put ESI tags in, say, an image. But then if you're able to have the first character of your image be a greater than symbol, then Squid just thinks everything is fair game. So then you can put ESI tags in the image and have that echo back to you. In terms of mitigation, we reached out to Christian Fellini, which is the co-head of the core rule set, which is the OWASP project for the Mod Security team. Give us like an anonymous shout out, because we wanted to have a way for security personnel to have a first line of defense on day 0, basically, after we released the blog post. And he was super nice to us, and he ran a whole bunch of test cases, and he turns out that Mod Security already detects ESI just through the fact that it's using XML subsets. So if you have Mod Security core rule set from OWASP, you're already golden. You're not going to be attacked by ESI anytime soon. So great project and great response from the co-lead. Now we'll talk about web cache poisoning, which is my favorite as of late in terms of how much you can find that in the wild. So earlier we talked about some sort of web cache poisoning in the sense that you could use ESI and line tags to poison cache entries using Oracle Web Cache. But that's kind of a niche subject, right? So you need to have ESI injection, and you need it to be sitting on top of Oracle Web Cache. It would be nice if we could do web cache poisoning on a large scale because of a flaw that is more of a specification flaw, right? And then that kind of happened this summer when security researcher James Kittle came up with his DEF CON or Black Hat talk, about practical web cache poisoning. And I highly recommend you go watch that talk. It's a 50-minute talk for which half of this 50-minute talk is just world case examples and like applicable world case example, and it has a lot of real world value. So please go watch that. Sorry about that. So what is web cache poisoning? So basically, it's a technique that is going to leverage unsafe or even sometimes unknown HTTP headers and couple that with caching so that you can have arbitrary code or arbitrary HTML or whatever be cached across all users. So briefly, we talked about caching and how caching works, and we said that the cache server would see the file name and then store a copy and then serve that same copy to everybody else afterwards. But when you think about that, that's like a naive way of doing caching, because in the modern web, sure, the file name is going to remain constant, but that's kind of the only thing that is going to remain constant, because browsers are different, languages are different, and even encoding are different. So what caching mechanisms came up with is the following way of adding kind of a variability to file names. So you're going to have what they call cache keys. And then instead of just storing index.php as its own individual cache entry, you're going to have index.php for this particular encoding and this particular language, for example. So in this example, the cache keys would be the file name, the encoding, and the language. And this allows you to store the same file with a certain level of variability. So every other header in this is basically unkeyed. So once this request is obtained by someone using, for example, an English not user agent, an English accept language, and their browser supports broadly, then the cache is going to put the response inside that own unique cache key. And then once somebody else requests the same file but with a French accept language and no broadly, for example, they're going to have another cache entry so that they don't basically get served across the same file. Because if the first guy that supports broadly requests a file and then another person requests the same file but don't support broadly, they're just going to get garbage sent back because the encoding is not right. So right, we have keyed input and unkeyed input. So when you think about the following request, we can see that the keyed input is going to be index.php, so the file name, and then the host is also a keyed input. So as you can see in the bottom, that's what the HTTP server sent back, and you can see that the host is being reflected back in the HTTP response. And that's pretty typical, right? Because you want your users to click on the link and remain on the same web host. You want the domain to remain constant, so people will use the content of the host variable, and that's fine. So that generates your first cache key, and then during your pen test, you run a whole bunch of automated scans, and you have no idea what you're doing, and then you find the following header, X forwarded host, and you realize that the content of the host header is now overridden with the content of the X forwarded host header. That's weird. You don't really know what X forwarded host is, but you know about caching, and you know that X forwarded host is probably not a keyed input. So that the next time that you request the same file without X forwarded host, that's weird because it's been committed to cache, and that's because X forwarded host is not keyed, meaning it doesn't warrant its own individual cache entry. So you just poison the content of index.php across all users, and the next time somebody else requests the same file, they're probably going to get your XSS payload back, and that's kind of dangerous. And we could be talking about what X forwarded host is or why it's important, but it's not really important in terms of this attack scenario because it's just one of the many cases in terms of having HTTP headers being reflected back in the response. So X forwarded host is just a way that the cache server is going to tell to the origin server which host header was used by the user. So when you think about it, you already have your three things. You have your user, your cache, your origin, and the host, when the user requests a file to the cache server, they're going to be a specific host. So for example, here you have app.com. But the cache server, when it reaches back to its backend servers, well, the backend server's host is not app.com. It's probably going to be stuff like app.prod01.corp or something like that. So the cache server is going to use that as their own host. So then how does the cache reach to the origin server and tell them which host was specified by the user in the first step? Well, it's going to do that through the X forwarded host header. But as I said, it's not really important that you understand this right now, and you should look into that if you're interested in caching exploitation. But there's a whole bunch of headers out there that are being used in the same way. Not always to overwrite hosts, but sometimes you'll have X debug, and that's something that the developers came up with that is going to print all of the cookies, and they're expecting nobody to find out about that. But if you brute force them, you will. Or even open source intelligence. Sometimes you can look at source code on GitHub and realize that they're putting the content of a header inside the HTTP response, and they forgot to put that as a cache key, meaning it doesn't warrant its own individual entry. So you can use that to have other people poisoned through potentially reflecting your own individual stuff that was committed to the cache. A single thing that you need to remember before trying this on, for example, public bug bounty programs is poison safety. And I love calling it poison safety. But basically, you want a way to test cache poisoning without affecting everyone, right? You don't want to be trying to get your XSS payload cached and then having everyone see your nice little XSS, because then bug bounty program is going to be pissed at you and you will get $0. So what you can do is using that same knowledge we just saw, which said that the cache entry is also the file name. So if you have index.php with a question mark foobar, for example, that is going to warrant its own individual cache key. So you're going to be able to poison your own URL. So here it's the same example where you have extroverted host and you have that committed to the cache. And then as you can see, index.php is just not affected. And then the next time that you do the same header, you did the same request. So with foobar, you remove the extroverted host header and you see that you poisoned yourself. And through all of this, you never impacted the other user because they have their own individual cache key. So by having a very unique parameter, a random parameter at the end of your file name, you're able to not impact everybody else. So that's a neat way of being safe in the way you poison. So the impact of web cache poisoning, I feel like it's still not quite known because it's very recent that we've been able to do this on a large scale, right? Before James Skettle's research, we all thought that was kind of, he uses the word unobtainable, but that's kind of the best word when you think about it, because nobody thought you could do it. And he came up with so much real world example that he proved us wrong. And that's what I've been looking at for the past, I don't know, month or something. And just the past week, I found two vulnerabilities very close to this on extremely popular bug bounty programs. And I say this because nobody is looking at this. And I want people to start looking at this because it's awesome. Like, people should be trying to poison cache. It's such a great vector for everything. You can even have a denial of service. So I found a weird edge case where if you added some header, I think it was X original host, the web cache would be completely confused and put a maintenance page. So it would say this website is down. But since the original header with which I did that is not keyed, everybody else's version of the site is also down. So through my own request, which I sent once, I poisoned the cache for everybody else, effectively shutting down the website for everyone. So that's a cool trick. So to find out about popular headers, you should look at Paraminer, which once again is developed by James Skittle. It's a great extension to add to your burp. It's accessible on the free and the paid version of burp. It's got a whole database of very popular headers that people will use. And it's also going to do the next step, which is trying to poison it using a safe parameter in the get URL. So sometimes you just run it on a bunch of URL and you end up finding actual cache poisoning entries. Often you'll be kind of limited by what you can do with them, but if you're creative enough, you can find very interesting bugs with cache deception, not cache deception, cache poisoning. So that's kind of what I have today. It's a very brief introduction, as I said, to cache attacks. This is 101, at best 102. So there's still a lot of research to be done with this, and not even research, like there's a lot of stuff to be applied to even public websites out there to find out about cool bugs that no one's found before. So please go out there and try cache attacks, and yeah, just reach out if you want any questions. This is my Twitter handle, DMs are open. So thank you for coming. I think there's some time for questions, but I'm not sure.
We have a question.
There's a question? Okay.
Yeah, thanks for the presentation. So during your sort of research and investigation, is there certain sort of frameworks or languages that are more susceptible to this attack?
In terms of?
The cache poisoning, the cache, sort of you said it was aggressive in terms of being able to store if you enter sort of, again, the JPEG example in the early beginning.
I'm not exactly sure what the.
So like, for example, you mentioned Django is susceptible,
Yeah.
or is, I don't know, some of the other major frameworks, major languages, are they more susceptible to this type of
Okay,
exploit?
okay, I understand what you mean. Not really, because when you think about it, it's always individual issues, and sometimes it's individual issues being coupled together. So the fact that Django was sending 200 OK to garbage file names is fine by itself. It's not a bug. It's the fact that Django does this weird little bug, which is just, it's not a security bug. It's just a technical, like it's not even a bug. It's really just, it's a feature basically. And the fact that this does this and that caching is too aggressive is just, it ends up working in our favor, but it's not like a main problem. So there's no really like, it's no one person's blame. It's just neat things coupled together, basically.
Okay, thanks.
Any other questions?
So what is the mitigation against that?
Against the web cache poisoning?
Yes.
There really isn't, right? Don't use headers that you shouldn't, right? Or at least if you're using headers, put them as cache keys so that if you do poison your own stuff, you're not going to poison everyone. So don't use obscure headers. I think James gave an example of using some framework that was based on Xen, the PHP thing Xen, and basically James reported a bug where there was this X original URL and he could have cross-site scripting cached and then streaming it back to other users. And then he reported that to the code maintainers, and the maintainer said, I just looked through all of my source code and this header does not exist. What are you talking about? And I can replicate this, so I'm not going crazy, am I? What's going on? And then they just realized that through dependency injection, they were using Xend, and Xend is the one doing this. So by using other people's code and not reviewing it, you realize that they are using HTTP headers that you had no idea. So imagine you're a sysadmin and you're responsible for the cache server. What are the chances that you went and you talked with every single developer that is using unknown, obscure HTTP headers for like debugging or benchmarking? It's not realistic. And that's why this bug is really more common than we previously thought.
Yeah, I guess when James reported it to Cloudflare, then they decided to remove some of the headers which they were expecting before while deciding the cache.
Yeah,
No
of
cache.
course, there's a bunch of headers that can just be disregarded.
Right.
Like you could even have at some point some sort of whitelist of headers, like just drop all of them because I don't care about them, and it kind of mitigates that. But I don't think that's been implemented, but perhaps you know better, I don't know. I need to look into it.
Okay, thank you.
Do you know if cloud providers like Amazon Web Services, CloudFront are looking into these types of issues?
Yeah, well, cloud providers, I don't know, but for example, when Omergil reported web cache deception, I think the next day or the next week, everybody had a blog post out. Like Cloudflare had to have something to fix this. Akamai had something to fix this. So they're all very receptive to this. I don't know about like actual research, but in terms of fixing these issues or mitigating them across all clients, yes, they're helpful. They're doing their part, in my opinion.
Any other questions? Oh.
So if we were interested in getting a lab environment to play with some of this stuff, do you have any tips, pointers, like where to go to play with some of this stuff in a way where we won't get arrested?
So edge side include injection, somebody made a vulnerable version. I think it's a Docker, I'm not sure. Okay. But it's on GitHub. It's easily findable on GitHub or even Google. Okay. For all the other ones, they're very easy to deploy. Just pick your cache engine, make a little PHP snippet or whatever you like, Node.js snippet, and just specify which keys you want, and then just abuse your own servers. It's a 1 hour project, really.
James got a lot of stuff too.
Right, that's true. His CTF game thing. Yeah, he has a bunch of challenges where you can try a whole bunch of cache attacks. I don't know how much it works. I heard that it crashes a lot because people hammer it, but yeah, good point. Yeah.
Okay, last call for questions. Great. Thank you very much, Larry.
Thank you.